Hello all. In this lecture we will see second part of database design. So in this lecture we will see formal guides. We'll before going to formal guidelines we will see what do you mean by this functional dependency, and also we will learn about keys. So you will see functional dependency, then what is meant by normalization, keys, what is super key, primary key, candidate key, secondary key, all these things. So this is very important. Then only you will be able to follow how to design this formally. So functional dependencies. So functional dependencies are actually constraints that are derived from the meaning and interrelationships of the data attributes. So it is actually it's a constraint. Functional dependency is a constraint between two sets of attributes from the database. If we have two sets of attributes, constraint means it's a functional dependency. It's a constraint or some condition that should exist. So it is used to specify formal measures of the goodness of relation designs. So this functional dependency is used as it forms a basis to say whether a relation is good or bad. Okay. So constraint between two sets of attributes. It is actually a condition between two sets of attributes. It may be a constraint between two attributes also. It may not be sets of attributes. It may be a constraint between employee SSN and employee name, or employee SSN and employee phone number. Okay, it may be a combination of sets of attributes, or it may be between two attributes. So functional dependency and keys are used to define the normal forms of for relations. We will see what is this normal form and all. So first of all, we will define a functional dependency. If we have a relation, we call it as universal relation. Universal relation with many attributes a1, a2, etc. an. So there are n number of attributes in this universal scheme. For example, if you are taking a college database, we have different attributes in that college. Student name, student roll number, faculty name, faculty pen number, faculty phone number, parent name, like that. There will be hundreds of attributes in that universal relation. So let the R be such a relation with n number of attributes. What is meant by functional? What do you mean by this functional dependency? A set of functional dependency. It is a set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y. So here in relational database systems, W, capital X, capital Y, capital Z all denotes set of attributes. So here X means it is a set of attributes. X is not may not be a single attribute. Then capital A, B, C, D, that is the initial letters, capital A, B, C, D are used to denote single attribute. Then in order to denote relations or tables, we will be using PQRS, like that. Okay, PQRS will be used to denote tables or relations. So here X, Y means it is a set of attribute. It is not a single attribute. It contains many other attributes. It may or may not contain n number of attributes. Okay, so it is a set of attributes. So a set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y, or we can say that Y is functionally dependent on X. If we say from X to Y, we say X functionally determines Y, and if we say reversely, we can say conversely, we can say Y is functionally dependent on X. So it is denoted by X arrow Y. So X to Y, we will be calling it as X to Y. So this means Y is functionally dependent on X, or X functionally determines Y. So definition is like this: between two sets of attributes. So functional dependency, it is between two sets of attributes X and Y that are subsets of R. So X is a set of attribute and Y is another set of attributes, and this X is subset of R, Y is also subset of this universal relation. X and Y that are subset of R specifies a constraint or condition on the possible tuples on all the rows, this condition should hold. The constraint is like this: for any two tuples T1 and T2 in R of R. So we have already seen this R of R. R of R means a particular database state. When we studied previously about this constraints, integrity constraint and all, we have already seen this notation R of R. So R of R denotes a particular table state in that table. That is the table. If that relations are table filled with some values, then it denotes a particular state. So if there are any two rows T1 and T2 in R that have T1 of x equal to T2 of x, if we take the x of x attributes of that row, first row, and x attributes of the second row, if it is same, then T1 of y should also be equal to T2 of y. Then their y value should also be same. Then we can say that y is functionally dependent on x, or x functionally determines y. Okay. So this is a condition. If any two rows or any two tuples exist in that relationship, in that state, then T1 of x equal to, if T1 of x equal to T2 of x, then if those row values, x values are same, then their y values should also be same. Then we can say that y is functionally dependent on x, or x functionally determines y. So we will see some examples of this functional dependency. Social security number determines employee name. So this is a constraint, SSN to ename. This means SSN functionally determines ename, or ename is functionally dependent on SSN. So when we take any of the tables, that SSN value, if that SSN value is 1, 2, 3, 4, 5, and if that ename is Abhiram, then whenever that SSN name occurs, that ename should be Abhiram itself. So then we can say that ename is functionally dependent on SSN. Project number determines project name and project location. So this can be denoted using this notation. P number to P name and P location. This means P name and P location is functionally dependent on P number. So whenever P number changes, that P name and P location also changes. Then employee SSN and project number determines the hours per week that the employee works on the project. This is another functional dependency. So hours is dependent on SSN comma P number. So this combination, so here we have a set of attributes. If we take, this is x and this is y here. So x is, even though we have mentioned that x is a set of attribute, here we have only a single attribute here. Similarly, y is having only a single attribute. But in this case, y is a combination of two attributes, p name and p location. Here, x is a combination of two attributes. So x is a set of attributes. So ours is functionally dependent on SSN and P number. It is the combination of this thing. SSN comma P number functionally determines ours. So SSN to ours may not hold, or P number to ours may not hold. This combination only holds. Okay. So a functional dependency, it is a property of the attributes in the schema of that R. It is actually a property of the attributes. So constraint must hold on every relation instance R of R. Whenever some updation occurs in that table, this constraint should hold. If K is a key of R, then K functionally determines all attributes in R. So we have already seen what do you mean by key. So K means it automatically functionally determines all of the attributes in that table, or all of the attributes are functionally dependent on that key attribute. If K is a key, K means it can be a single attribute or a set of attributes. If K is a key of that relation, then K functionally determines all attributes in R. Because we cannot have these two distinct tuples with T1 of K equal to T2 of K. It can never happen. T1 of K will never be equal to T2 of K. Okay, no two rows will have the same key value. So this is an example. If you see this, all this functional dependence will hold, because here SSN is the key of this relation. So all other attributes, that is e-name is dependent on SSN, birth date is dependent on SSN, address is dependent on SSN, department number is also dependent on SSN. So if we take this table, also D number is a key. So D name and D manager SSN is dependent on D number. So if we take this table, D number, D location, this combination is the key. So if we take this combination, this is a key. So D number, D location is dependent on itself. Okay. So this is another example. Teach relation. We have teacher, course, and text. We do not know which is the key and all. So this is the R of R, or the state, our relation database state of this thing. Now, if we file, when we see this database state, we can determine some functional dependency. So one functional dependency we can see is text to course. Text to course, there is a functional dependency because bottom bottom text is or course is functionally dependent on course, because if we take t1 of x, t1 of x is bottom, there is no bottom again. Whenever bottom occurs, data structures will be there. Then another t1 of x is Martin, it is always database management. Whenever Hoffman is there, it is always compiler. Whenever it is Horowitz, it's data structure. So text to course, course is functionally dependent on text, or text function determines course. When we take teach to course, there is no functional dependency. Teacher to course, there is no functional dependency, because when a teacher, we have Smith. In one case Smith, we have data structure. Here another Smith, again it is another subject, it is another course. So t1 of x is equal to t1 of x, t2 of x, but t1 of y is not equal to t2 of y. So this functional dependency is not there. Then if we take text to teacher also, there is no functional dependency, because we have t1 of x here, but here if we take, there is Smith, again we have another t1 of x, t2 1 of x, but we have the same t1 of y. So there may not be any functional dependency between text to teacher. Similarly, there is no functional dependency from course to text also. We have data structures here. We have t1 of x equal to t2 of x, but t1 of y not equal to t2 of y. So there is no functional dependency here also. Okay. So defining functional dependencies from instances. So in order to define the functional dependency, we need to understand the meaning of the attributes involved and the relationship between them. Then only we can say that functional dependency. So if an FD is a property of the attributes in the schema R. So given the instance or population of a relation, we can conclude is that a functional dependency may exist between certain attributes. Okay, we can say that some functional dependency will say what we can definitely conclude. We may not be able to conclude this thing. We can definitely conclude is that certain functional dependency do not exist because there are some tuples that show a violation of those dependencies. So this can be determined. So if we have a populated table, or if we have a relationship instance, or if we have some table, from that table we can definitely conclude that some functional dependency do not exist. But we cannot say that that functional dependency may exist. We can simply say it may exist. In some other new row is added, that functional dependency may be violated. So this is an example. We have a table ABCD with its extension. So this is the extension of this table, or the state of that table. So from this we can conclude there is no functional dependency from A to B, because we have same A value here. A1 and A1 is same, but B1 and B2, this is different. So A to B, there is no functional dependency. Similarly, from B to C, there is no function. There is functional dependency. B to C, there is functional dependency. If from D to C, there is no functional dependency, because D3 we have same X values, but Y value is different here. So the D to C, there is no functional dependency, and like that we can conclude which all functional dependencies are not there. So if A to B, there is no functional dependency. Similarly, from B to A also there is no functional dependency because B2 and B2 is same, but that functional dependency is not there. Here A1 and A2 are different. So B to A and D to C, there is no functional dependency. From this table, it can be concluded that B to C and C to B, some functional dependency is there, but it may exist, but if some more rows are added, that functional dependency may not exist. Okay. And also we can conclude this combination is also there, A comma B to C, this functional dependency is also there. You can simply check when this combination occurs, A1 comma B1, that combination occurs, then always C1 will be there. Okay. When A2 A1 comma B2, this combination is there, then this dependency, that C2 will be there, or A2 comma B2, that combination is there, then definitely it will be C2. A3 comma B3, then C4 will be there. And also A comma B to D also exists. Whenever that combination occurs, D is functionally dependent on A comma A and B. Okay. So these functional dependencies, so what we have written is these functional dependencies may exist. Okay. But we can definitely conclude that this functional dependency is not there. This this may not be correct, because in this case this is correct. If we have some more additional rows in this table, this might get violated. Okay. So this is another functional dependency. You can check, you can verify with this table, with this instance. So normal forms based on primary keys. So before going into this normalization of this relation, practical use, we'll be learning about this normalization. What is meant by normalization? What's the use of this normal forms? Then we'll learn about definition of keys and attributes participating keys. In the next lecture, we'll be learning about first normal form, second normal form, and third normal form. So in this lecture, we will see all these normalization also. So normalization, it was first proposed by Code in 1970s. So it takes a relation schema through a series of tests to certify whether it satisfies some certain normal form. So we will simply check the relations with some conditions. If it satisfies these conditions, we will say that this particular table is in this normal form. It's a top-down fashion. We will be doing this relational data designed by analysis. Just a minute, it is actually relational database design. So in the previous lecture, we have already seen this relational database design by analysis, and there are two ways. One is top down and bottom up. So here it is top down fashion, so it is known as relational database by analysis. Initially, Code proposed three normal forms. So it was Code who proposed three normal forms: first normal form, second normal form, and third normal form. So a stronger definition of third normal form was BCNF is there. BCNF was proposed later by Boyce and Co. So what we do is we'll first check whether it is in first normal form. If it is in first normal form, we will check whether it is in second normal form. Then we will check whether it is third normal form. So we'll learn about this normal form in the next lecture. Before going into this normal form, we will try to see what is this normalization. Normalization means it is a process of decomposing unsatisfactory or bad relations by breaking up their attributes into smaller relations. So we will start from a table and we will check whether it satisfies some conditions. If it is not satisfied, what we will do is we will decompose, or we will split into two or more tables. We will split it into two or more tables or two or more relations and check again whether it satisfies those conditions. So process of analyzing the given relation schemas based on their functional dependencies and primary keys to achieve the desirable properties of minimizing this redundancy and minimizing this insertion, deletion, and updation anomalies. So this process is known as normalization. So what we do is we will analyze the relation schemas based on the primary keys and functional dependencies so as to achieve the desirable properties of minimizing this redundancy. When we minimize this redundancy, we can minimize this insertion, deletion, and update anomalies. So normal form definition refers to the highest normal form condition that it meets. So when we say that a particular table is in third normal form, it means it satisfies those conditions of that third normal form. So indicates the degree to which it has been table. So it has been normalized. So if we say this table or these relations are in third normal form, it means that it has been normalized to that level. So we'll learn about this in the next lecture. So condition using keys and functional dependencies of a relation to certify whether a relation schema is in particular normal form. So when we say this, it is in third normal form, we see that it satisfies some condition based on those keys and functional dependencies. So additional properties may be needed to ensure it is a good relation schema, that is lossless join. We have already seen the previous lecture, and dependency preservation property. So we will see in the later lectures also. So why do we use this normal forms? So the normalization results in the designs will be of high quality and meet the desirable property. So when we normalize, it will satisfy the desirable properties. That is, lossless join and dependency preservation property will be there, and also the anomalies won't be there. Okay. So the resultant designs will be of high quality and it will meet the desirable properties. So these normal forms are constraints on which they are based are hard to understand or to detect. So these constraints on which they are based are actually hard to understand or it is hard to detect. We need not normalize to the highest possible normal form. Usually we will be normalizing up to third normal form or sometimes up to BCNF. There are other normal forms also. Fourth normal form, fifth normal form is there, but in your syllabus you have to learn only up to BCNF. We need not learn fourth normal form or fifth normal form. So denormalization means it is a process of storing the join of higher normal forms relation as a base relation, which is in lower normal form. When we try to reverse that process, we call it as denormalization. We need not worry of the definitions. Only thing we have to notice, normalization means it will result in designs of high quality tables, and also those desirable properties will be satisfied. So we will try to normalize into some normal form. There are different normal form. First normal form, second, third, then BCNF is there. Fourth normal form, fifth normal form is there. We try to normalize at least up to third normal form, and maximum maybe sometimes we will be normalizing it to BCNF also. So in this lecture, we won't be normalizing, seeing that normal forms. We'll be learning about keys and attributes, about different kinds of attributes also. So we'll be seeing first definition, super key. A super key of a relation schema R equal to A1, A2, etc. N is a set of attributes S which is a subset of R with a property that no two tuples T1 and T2 in any legal state R of R will have T1 of S equal to T2 of S. So we have already seen the super key. So super key of a relation schema R we have, it is a set of attributes S. S is a subset of this R. S is a subset of R, and it should satisfy this property, that is no two tuples or two rows T1 and T2 in any relation state R of R will have T1 of S equal to T2 of S. Key, this is super key. Key is a key is a super key with the additional property that removal of any attribute from K will cause K not to be super key anymore. So you will see an example, then you will understand. So SSN is a key of employee, whereas SSN comma SSN ename, SSN ename comma B date, and any set of attributes that SSN are all super keys. Here SSN is a super key. SSN itself is a key. Here SSN is a key of that employee. SSN is a super key. If we take the combination of SSN comma ename, it is also a super key, but it is not key because we can remove ename. Still we have this SSN. Or similarly SSN comma ename comma birth date. This combination is a super key, because it satisfies that property. This property is satisfied. But it is not key because we can remove ename and bdate and still we can uniquely identify. Okay, so that's the difference between super key and key. So all keys are super keys, but all super keys may not be keys. Okay. So if a relation schema has more than one key, then each is called a candidate key. If there are more than one keys, then all those keys are known as candidate keys. So we have already seen this in the previous when we learned relational algebra, what is super key, keys and all. You can refer that lecture also. So if a relation schema has more than one key, then each is known as a candidate key. So one of the candidate keys is arbitrarily designated to be primary key. Then the other keys are called secondary keys. So you should know what is a candidate key. There can be more than one key in a relation. Then all the keys are known as candidate keys. One of them will be kept as primary key. Then the other keys are known as secondary keys. Then what do you mean by a prime attribute? Prime attribute must be a member of some candidate key. If it is a member of any of this, if an attribute is a member of any of these candidate key, then it is known as prime attribute. A non-prime attribute is not a prime attribute. That means it is not member of any of the candidate keys. Then it is known as non-prime attribute. So all these definitions are important. So super key, then candidate key, then primary key, secondary key, what is this primary attribute and non-prime attribute. So if we take this example here, SSN is the primary key, then all other attributes are non-prime attributes. In this example, we have D number and D location. These two attributes are prime attributes. Okay, in this example, we have SSN, P number and hours. SSN is a prime attribute, P number is a prime attribute, and hours is a non-prime attribute. Okay. So if we take another example, student, in this table we have admission number, register number, Aadhaar number, roll number, name, date of birth, address, phone number. Here admission number is a primary is we have different keys in this table. Admission number is unique, so it is a key. Register number is unique, it is a key. Then Aadhaar number, it is also unique, so this is also a key. Roll number, it is also unique. So all these are known as candidate keys. So admission number, register number, Aadhaar number, roll number are all known as candidate keys. So we have underlined one of the candidate keys, admission number. So admission number is considered to be the primary key of this relation. So the other keys, register number, Aadhaar number, roll number are the secondary keys of this relation. Okay. Then if you take the combination of admission number comma name, this is a super key. This is a super key because it uniquely identifies. But this is not a key because we can remove this name and admission number uniquely can be used uniquely to identify. So this combination is a super key, but it is not a key. And similarly, register number comma phone number. This combination is also a is a super key, but it is not a key of this relation because we can remove phone number and we can uniquely identify. Then admission number, name, comma, date of birth. This combination is a super key, but this is not a key because we can remove name and date of birth, and with admission number itself, we can uniquely identify a particular student. So this is admission number is a key, and this combination is a super key. So this is a reference. Thank you.